One announcement first, I guess is probably more of a question than an announcement, is that the computer's talking back to me. There are a couple of students that are looking for presentation slots, and I'm starting to hear that maybe a few people are not planning on giving presentations that they're signed up to give. So if you're on the schedule for the rest of the semester, please let me know so that I can take you off the schedule so that I can add in anybody that needs to be added in, okay? So please come and see me after seminar today. Okay, today I'd like to introduce Muruganandam from the Indian Institute of Soil and Water Conservation. He is a visiting Fulbright scholar here working with the USGS co-op unit, primarily Steve Chips. He has over 20 years of experience in fisheries and fisheries management in northern India. And he will be here for about 18 months, and he's looking for interactions and collaborations with people here in South Dakota. Today he's going to talk with us about soil and water conservation research and technologies in India. Oh, I have to start the, oops.
Thank you for the introduction, and thank you all. Very good morning to everyone. And today it is just I just wanted to get introduced to you all and introduce what we have been doing in India, and just a glimpse of particularly on soil and water conservation research and technologies in the Indian subcontinent. And I'll try to do some, I hope that I will be able to do justice on that topic, and it's a very wide and vast.
Forward and back.
Oh, that's all right. And I have the problem of communicating with you, accent and all. I'll please try to excuse, and I'll be try to be slow, and we'll get you. We'll interact further. And the idea is just to have interaction and just to introduce myself to you people here, and introduce our subject, what you have been doing there. That's all. Thank you. And as far as India is concerned, India is a very vast country with diverse natural resources and different agro ecosystems, and it has got rich natural resources. Like we are having something around 3 to 9 million hectares overall, and population also over 1,000 million only, and the rainfall we have got sufficient. It's well over the world average, 117 centimeter annually, and that gives us 180 million hectometer of water resource. Groundwater also equally good, 60 million hectometer. Livestock population, that is 45 million, which is 15% of the world population. And flora also, we are rich with the diverse agro biodiversity. And as regard to water availability also, we have got a good amount of water resources. Basically, we are a monsoonal country. We are governed by southwest monsoon and northeast monsoon. And southwest monsoon during this monsoonal period, say July to August, is a very prominent water source for us. And that gives, with that we get something around 4,000 billion cubic water BCM. Okay, thank you. So, and this put together, and with this, this gives 690 BCM, river and surface water, and groundwater is 430. And with that, per capita availability is constantly reducing also because of our increase in population and demands from different sectors. And overall Indian per capita availability seems to be this 2200 cubic meter, and Tamil Nadu it is even lower, and it varies with the states and regions. depending on the population and pressure over there. And we are from Uttara Basin, and world average is this, and we are well below the average, world average level only, and even Asian level. So as regard to water resources and water demand, we are almost presently we are convenient, we are comfortable with the available rainfall of 1100 centimeter, that is 1100 millimeter. But we are likely to be stressed in coming years and decades due to increase in population and demand. And the main problem could be, all right, you are getting me, or I can continue like this, hai na? Comfortably. Huh? So we are present. I am making myself comfortable, hai na? So that I can be better interactive. Huh? Okay. And India is, you see, India contains many lots of countries. You see, within this is our geography, and in that is almost 10-15 countries are occupied in that in terms of population. Huh? So it supports something around 16 to 18% of the world population and 15% of the animal population, with just 2.4% of the world geography, world land mass, and 4.2% of the water resources of the world. So there is a lot of pressure. So you see everywhere people, and for everything queue, and everywhere people. That's our main concern, our main problem could be population, and our government is addressing towards that, and that is one side of our story. And that being so, then we need to advance our technological things and management, resource management issues, and how best we can manage our resources. That's how our government is striking. And in that, our ICA, Indian Council of Agriculture, is helping with agricultural technologies that we will be discussing further. And this is just to highlight the pressure of population and resource demand in India. And if you see United States, somewhere it is constantly, this population, we were in way back in 1940, we were 30 million people. Now that we are over 100 or so, we are just growing. 1.2 billion is the whole population. So India supports something around 1.2 billion of whole population, and it is likely to be 18% also. And just to 2.4 million land mass. That gives our pressure. And pressure and resources on demands on resources and subsequent land degradation. And it's a land degradation, though it's a global concern, India is having even more big problem. And this soil land degradation and silt load in our basins is a big concern for our country. So this is a global context of degradation also, just to give you a comparative picture how this land degradation happens in different parts of the world. And here subsequently, what would be the world population sequentially, and what would be food demand by 2050. So there is an increasing pressure on natural resources world over, and which is more in Indian context, and that creates all land degradation problem. And in India, it is something around 120 million hectares are reported to be degraded due to different causes. Maybe water erosion. Water erosion is the major cause, and something around 80% of this 120 million hectare is caused by water erosion, the runoff and soil loss, all that. And subsequently, wind erosion is of course minimum, and chemical degradation like salinization and alkalinization, salinity of water and land is another cause of concern of land degradation. And put together, we have 120 million out of 320 million hectares. And this is just different categories of land degradation in a pictorial form. And this land degradation invariably affects our land mass and physiography and land resources, and ultimately agriculture production and food production. And this again, floods and drought becomes a major cause of land degradation in our country due to this varying distribution of rainfall temporally and spatially. Here if you see that 50%, 52% of the country receives over 1000 millimeter rainfall, and 32% between 500 to 1000, and 16% area receives only 15 below 500 millimeter rainfall. And majority and maximum rainfall occurs within a limited duration of time, that is intensity is high. That heavy spells occurs within 20 to 30 hours, which makes a lot of problems. If you see, in 2013 we had a very massive flood in Uttarakhand. People used to visit this Kedarnath temple. It's a religious temple in India, northern part of India in Uttarakhand, and people from all over the world and all over India used to visit every year. And during that particular few days, 13 to 14 to 17 June, the initial period of monsoon. This is the beginning part of the monsoon. People would not have thought of this much flood and rainfall and flood. And unexpectedly it has come, and lot of damage to the women and livestock and natural resources. So this is one scenario, and this is in Chennai also. This is in rural part, in hilly areas in Uttarakhand, and this is a well-developed town and Chennai. There also in 8 to 10 November, this is during northwest monsoon, we had a heavy flood. It's all because of unmanaged or unplanned urbanization and expansion of development happening in different parts of the country. And even in agriculture also, we have got runoff and soil loss related impacts on production and land degradation and due to different gully and rill erosions. And this is one part of the side, and we have got drought and dry land areas also. Problem of drought and dry land also causes. So this flood and drought alternates in the different parts of the country, and for which we need to have a different managerial efforts. And we have just categorized different categories of soil erosion by water, that is rainfall and runoff induced erosions. And we have categorized different soil erosion rates, 0 to 5 and above 80, and this in different category of erosion and different range of landmass falls in, and the maximum falls in 5 to 10 per hectare in majority of the area, and which is at the moderate scale also. And again it is this very high and severe, very severe also, not less, and this much around something around 1,60,000 square kilometer is also been affected by water erosion. And roughly, if you see different parts of the country and how do they experience soil loss and runoff and soil loss. And this is northern part Himalayan forest, and this is Shivalik down below the Himalayas, and Indo-Gangetic plains. It's where the Ganga river flows, and in that Indo-Gangetic plain it will be even more heavy soil loss, and that forms the Indo-Gangetic alluvial plains as well. And of course northeastern Himalayas adjacent to China borders, and these western parts of Gujarat. These are all different landscapes and regions of the country. Red soil in some central parts of India, and black soil southern parts of India, lateritic soil in Punjab and Haryana are very common. And these are different land resources, and their area in 1,000 square kilometer, and varying ranges of soil loss. And what would be what are the major land uses followed there. And the maximum could be here, artisan rate, and this black soil loss, square kilometer. And we have categorized different states, the land masses of different states for moderate and severely moderate and severe and very severe range of soil loss. And this indicates total over 10 tons per hectare per year soil loss in different parts of the states, and which something works out to be 38 total 38 million tons. And erosion losses under different cropping patterns in Doon Valley. So we study different patterns of erosion with respect to slope and different crops and cropping patterns and land geographic situations, soil depth and slope and rainfall. All that we study the rate of erosion in relation to crop and land geography. And this is one some example that what we do in so what is the impact of slope on crop production and soil loss and runoff. Runoff means nutrient loss as well. And we have prepared soil loss tolerance limits and for different states of the country. And based on that, we have come out with priorities, soil loss on soil management priority areas. It's arrived at potential erosion minus soil tolerance, T value. So that indicates the priority area for management. And of course, consequence. Oh, sorry.
I just have a question. Is with the soil laws, was it with tilling agriculture, classic agriculture?
Yeah.
Is that the standard?
Yeah, that we have got. I'll be just coming also. Tilling and conservation agriculture. We have got different treatment. Tilling and no tilling, conservation agriculture, and what would be the input biomass input, mulching, and different treatments. And that I'll be coming also. This is just it's a kind of introduction only. I'll just another 15 minutes. I'll just wrap up. Okay, thank you. And erosion, as we all know that erosion has got more of negative impacts, isn't it? And you do have some positive impacts in that sense. It forms of alluvial soil and construction material also. And this Indo-Gangetic plain is a major zone which is the fertile land. It's again formed by the erosion only in India, and which is the zone of more crop production in our country. So it could be the positive impact, but we have got more of positive negative impact that we need to bother much and we need to manage. That is where we come in. And then again, if you look at the constraints in adoption of natural resource management and conservation of agronomy, agriculture technologies, that our country is very diverse in terms of agroclimatic situations and topographic situations and different altitudes and slopes, because we have got different agroeco regions like this is Indo-Gangetic plains, and this side is the Himalayas, and these are all Himalayan states only, Jammu Kashmir, Himachal and all. And down below this is Punjab, Haryana falls under Indo-Gangetic plains, and eastern this is Eastern Ghats, this side Western Ghats, and there are varying range of physiography and soil resources, and accordingly variable soil fertility and more of rainfed farming. Here if you see 60% of our cropped area is rainfed, that contributes only 45% of our food production. And with 40% of irrigated area, we get 60% food production. With only 40% of irrigation, we get 60% food production, and again with only to 80 to 50% of irrigation efficiency. So there also we need to increase the irrigation as well as irrigation efficiency as well. And major our food production comes from the rain-fed agriculture, which is something around 60-65%. And our land holding is very small. Maybe 80% of the farmers own less than 1 hectare area. That also again gives problem for consolidation of farming and implementation of various technologies. And competing demands of agriculture for crops, and we have got many different sectors which competes for land and water resources. So agriculture is viewed least, though we are having pressure to produce more, but many sectors compete over agriculture for land and water resources. And within agriculture also we are focusing on few crops, and competition exists. That brings a question how to justify and harmonize and distribute our resources, and land degradation of course. And see slopey lands bring this was 400 mm rainfall occurred in 16 June 2013, that has caused a flood in Uttarakhand. So slopy lands bring a lot of soil loss and runoff, and that creates havoc at times. So all that makes our agriculture and NRM technologies to be problematic. So with that, to address those problems, ICAR, the Government of India, has instituted an Indian Council of Agricultural Research, ICAR, which is parallel of USDA here in US, and which has got this many divisions: crop science, horticulture, NRM, and engineering, agriculture engineering, animal science, fisheries, and extension education division. These many divisions are there, and it has some 4 deemed universities, like one for IRI, agriculture, and one for fisheries, one for animal science. There are 4 deemed universities and total 64 national institutes. They are all governed by these divisions of ICAR, and they are national research centers 15, and national bureaus 6, and directorates or project directors 13. And other than that, there are many all India coordinated research programs. Every crop has got some all India coordinator programs, on cotton, wheat, like that, and network projects. And other than that, we have state agriculture universities like these. We have got 63 spread across the country. And other than that, Krishi Vigyan Kendra, these extension centers, they are all again attached to universities and our national institutes like these. And all these set up govern manages the agriculture research and technologies in India. And under NRM of the ICAR, and we have got this many 15 institutes and NRM, and one is ours, Indian Institute of Soil and Water Conservation. We are located in Dehradun. And likewise, we have got many institutes like soil survey, land use planning, soil science, soil salinity research, and research complex for eastern region, water management institute, dryland agriculture institute, arid zone research institute, Indian integrated farming, Indian Institute of Farming Research, that is mainly addresses integrated farming system research, weed research, coastal agriculture research, coastal area research, and again the complex region for northeastern Himalaya, agroforestry research institute, and abiotic stress management institute, and this recently formed organic farming research institute. Like that, we have for different region and different commodity and different resources, we have got different institutes under NRM. Likewise, other divisions also have crop science and horticulture and animal science and fisheries. We have got many institutes, and here we are soil and water conservation research. And if you look at the history of the soil and water research in India, it started in the, we go by plan period. Every year India has got 5-year plan period. It started with the independence 1947, and roughly it's initiated during 1950 onwards. We have got 5-year annual 5-year plans. And the historical interest on soil and water conservation and watershed management started way back in 1943, establishment of this Royal Commission on Agriculture, 1980 to 28, and subsequently we had a interest on funding and improved agronomical interventions, leveling interest in 1943, and during this time 1930 only 35 US that started that soil conservation service, and we are also contemporary to think of soil and water conservation and watershed management during that time. And establishment of the Damodar Valley Corporation, River Valley Corporation subsequently followed during 1950, and with that we have initiated large scale dams and irrigation projects. And first and this was pre-plan period, and first and second 5-year plan focused on small watersheds, and series of soil and water conservation research and demonstration centers was established during this period 1950-54. And because soil and water conservation and watershed management was a major issues during that time, and during that time that many centers in different parts of the country was established, and subsequently moisture and water conservation was added to soil and water conservation practices, and water harvesting was emphasized. And fifth and sixth period plan around 1974, all those centers which were created during 1954 was reorganized into institute. The present day Indian Institute of Soil and Water Conservation was established in 1974, and that had many operation research programs and different area specific research interests. And then we have watershed management programs subsequently came up, because the Indian Institute of Soil and Water Conservation was pioneering in importance and techniques of watershed management, that we will be coming a little bit later. And based on that, Government of India started series of watershed management program during this time, and a national watershed development program, development projects in rainfed areas was started. And now database creation, compilation, and introduction of fisheries and animal science also happened in during this 8th and 9th plan period. And now this present government has reconstituted or clubbed all the agricultural schemes and programs into one single program, like Pradhan Mantri Krishi Sinchai Yojana, matlab Prime Minister's irrigation scheme. So all that watershed management, soil and water conservation or agriculture development programs are converged into one single program to monitor the efficient flow of fund and efficient work distribution and monitoring. And this is the whole history of establishment of Indian Institute of Soil and Water Conservation in Dehradun, and it has got 8 research centers established in different locations and different timings, depending on specifically address their different problems of the region. Like Kota Center is their ravine problem is ravine erosion and land degradation due to ravine is very more. And Bellary in Karnataka is having a lot of black soil problems, infiltration problems, and drainage problem is more. So there to address the black soil problems, and we have got a center in Bellary, and southern in Ooty, southern region of India, we have got to address the problems of hilly regions in southern India. And Agra also, it addresses ravine area, the Yamuna ravine. And Chandigarh, we are aiming to address these Shivaliks and foothills of Himalayan problems. And Bundelkhand is a dry area, and to tackle the dry land situation, we have got a center in Bundelkhand. And Koraput, again the eastern part of India, which is again suffers due to shifting cultivation and land degradation, and we have got center here. And it means that we are 7 put together 8, 9 center, including Dehradun headquarters, and we address all parts of the country for natural resource management and soil and water conservation research. And we work in 7 research teams. Now we have clubbed into 6 only, and these 2 we have put together. And our main aim was water erosion, that is soil erosion due to water. Its appraisal in different agro-eco regions, and conservation measures for sustainable production in arable land and non-arable lands through different soil conservation and agronomic measures, bioengineering measures. And hydrological behavior of watersheds for conservation planning and implementation, particularly small watersheds. How do they reflect for our soil and water conservation measure implementations? And to understand the hydrological behavior, it's mainly engineering aspects and modeling and such programs. And rehabilitation of area affected by mass erosion, particularly torrents and landslides and mine spoil area rehabilitations. So area affected by mass erosion, and integrated watershed management. We address, we promote participate integrated watershed management with multidisciplinary interest of agriculture, horticulture, forestry, agronomy, and fisheries, animal science, and social science. So we promote integrated watershed management. We take up projects under this category in this area. And of course, socio-economic and HRD, human resource development. These 6 areas we are focusing. And we have got 4 divisions. And first one is soil and water, soil science and agronomy. Presently, we have completed many programs, and presently these many programs are ongoing there. Impact of soil erosion and climate change, and the dynamics of soil carbon through tracer techniques, CCM 136 they use, and erosion of soil as a source and sink of atmospheric carbon, and they have got some simulation and modeling studies. And rainfall data is used to prepare intensity, duration, frequency details, and isotope hydrology to study the rejuvenation of springs using isotopes. There's another study going on with another institute in collaboration with another institute, Body Institute of Himalayan Geology, on erosion productivity relationships. They are coming out in different geographies, different slopes, different depth of soil, what would be the production for given rainfall, all that. And the role of soil and water conservation techniques for resilient agriculture, and this is plant science. Again, various plants and vegetation, how do they help for soil and water conservation? Silvicultural measures, agroforestry and cropping patterns for different land types and agroecosystems, and introduction of horticulture-based and plant-based rehabilitation of degraded lands, and how to use the degraded land for different agriculture purpose or production purpose. And they experiment with planting techniques, canopy management in different crops, pruning and pollarding, all that, leaf litter management, and using different bioengineering measures and different biocultivars. And hydrology engineering division addresses soil erosion fluxes, and again establishes erosion productivity relationships, and it works on climate change hydrology, and soil erosion map is also under preparation. User friendly decision support systems and computer based decision support systems are being developed, and they address impact of extraction of riverbed materials for construction and different purposes. How do they impact river bores, and what should be the method of extraction of riverbed materials? They guide state governments and other stakeholders in extracting riverbed materials. And of course, aquaculture and fisheries, that is where I am focused there. And this is just this is a hydraulic flume to simulate the riverine course, so that devise suitable spurs and retards, and how these rivers can be drained, and soil erosion, riverbank erosion can be controlled, all that. And this is one of the example of geojute application to control landslides. And of course, human resource division, management division, it takes up long-term and short-term training courses. We have got 6 months, 4 to 6 months long-term training courses on soil and water conservation and watershed management, covering all aspects, mainly multidisciplinary interventions. And besides short-term few weeks courses also we take up there. And this institute promotes watershed management, that we all must be knowing what is watershed management, what are all components could be involved in using different multidisciplinary interests. So we promote participatory watershed management. Of course, we need not focus on those things, and this is just how do we go about in effecting integrated watershed management program. We progress through these many techniques that we may be well aware of. I'll just skip through, and all these things we will work capacity building, all we take up this. And again, what would be the approach and technique to tackle the erosion problems and erosion control intervention. And we mainly focus on land configuration measures in arable lands, and again non-arable lands means hilly slopes and riparian zones to rivers, and mining areas and mass erosion eroded areas, torrents. And we adopt this many brushwood, loose boulder that we will be seeing later, and of course agronomic measures and vegetative barriers also include that. And we propose alternative land use management based on natural resources available and soil quality there, and different agroclimatic situations there. and of course water harvesting, recycling is our main emphasis there. And we prescribe land configuration techniques like contour funding for what should be the different techniques for different land slopes. If it is a slope is 0.5 to 6 and contour funding, and subsequently graded funding if it is up to 8% slope, and bench terracing in steep slopes, and conservation bench terrace that will be coming. And similarly we will be we are doing contour funding, different types of funding, and that includes contour funding and bench terracing, conservation bench terracing, and grass waterways and conservation ditches, all that. And these are some photographs to view for our own understanding, contour funding and funding along the contours, and different funding. If you see this contour and side bund, lateral bund, and staggered bunds, and these bunds are placed in a staggered manner, and this is a bench terrace in hilly areas and slopes, and this is again terracing only in the hilly part of the country, and this is conservation bench terrace. We just level the lands, and this applies in a mildly sloping areas in 2 to 10% of slope. And we level these, if the slope is naturally existing, we can make use of that. Otherwise, we may level the area to have this mildly slope. And in that, we'll divide the area into the two regions, upper regions, that is highly upper region of sloping region, and that is a contributing region, and that receives that gives the runoff, and that generates runoff, and that runoff will be harvested or impounded in the subsequent receiving portion. This portion will divide into upper contributing area and down below receiving area, and there in the upper region we may plant crops requiring drainage, less water loving crops, and in the down regions we may plant more of water loving crops like paddy, all that. And the end of the plant we can harvest the water down below, and which can be again used for fish farming and integrated uses, and we can again irrigate irrigate back to these crops in the upstreams during summer or water stress period. This is the plan of the conservation bench terrace. This is contributing area, and which is the down area we have made a impoundment that can be used for multi-purpose. And this is the mechanical measures. This is normal. This is measures followed for non-arable lands. So this is brushwood check dam and loose boulder check dam. It is all again depending on the availability of material in a given locations. And because we don't get these stones and materials to block the runoff, so that reduce the velocity of runoff and erosive force of the runoff. So depending on the availability of material and land physiography and geography, we propose these land boulders check dam and brushwood check dam, and series of gabions. This again retarding the flow of runoff, that improves erosion situation. And this is drainage line treatment structures. And again, these are all gabions only. And the different ways, rectangular ways and retaining ways, drop structures and diversion wall. These are all different ways which are used in conduiting runoff, rainfall runoff, so that erosion becomes minimum, and the sediments are trapped for redistribution to the source behind. And these are some gully plug structures, and this is an earthen dams to impound the runoff, and so that reduce the erosivity. And this is gabions erected along the river courses, so that stream bank erosion is controlled, and this river flow is regulated, and maybe due to reflecting type of these spurs also different types of reflecting and attracting, all that depending on the situations. And these are all placed in mainly in eroding rivers and torrents. And these are some of the pictures of how these torrents erode the river banks and agricultural lands, adjacent agricultural lands. And this this is gabion and the trapping of sediments just behind the gabions, and a series of gabions placed in river courses for river training and erosion control. And this is one another technique, attack rate. I'm viewed all right? Sudhir? Sir? Going good?
Yeah.
Okay, thank you. Because I am also new to the system and to the subject and to the people, and I may have a bit of trouble, but please bear with me and we'll go ahead. Okay, this is another technique that katak rate, where we don't have loose boulders to build gabion structures or barriers or spars. We can use these bags. This is used cement bags, and in that they have got a different combination of cement and sandstones there, and we can fill these used cement bags and leave it for overnight, and that become a stone material that we say katak rate, and it is used to again used as a spar or retarding gabion structure. And this is one model that we tried these katak rates. This is again gabion structures only. Okay, and this in the upper portion you see adjacent to this is cropland, and this is a river course and this river course engulfs agricultural lands, and the farmer and adjacent people were worried so much, and we have placed the bund or small road come bund across the river. This is the second photo, left side you can see, and there with that this erosion, this land cutting along the river course is stopped, and this river, the same river is also trained to have a normalized flow using these katak rates again, and the katak rates are placed in gabion in the form of gabion structure, which improved the agricultural land system, and people are also had a good conveyance. Otherwise, the crossing and road crossing and reaching villages was problem there earlier. And landslide treatment using geojutes. Geojutes is nothing but knitted synthetic textiles, coir material, and they are layered in the landslips and landslide areas, and seeded with local grasses or suitable grass species there. And within it is done prior to monsoon, and next monsoon you get a lush green growth here, and this geojute also disintegrates and it stabilizes the landslides and slopy areas. So this is a treatment of eroded land with geojutes and coir jutes, geotextiles. And we have taken up one example of mass erosion control. We have selected our own watershed, and I will be seeing some of the slides subsequently. And these are different details that how much runoff and soil loss is happening there. It is something around 4,000 tons also per hectare in steep slopes in this part of the country, mainly due to limestone mining. Of course, now Government of India has banned there due to a fragile ecosystem. This banning mining for limestone is banned, but that area is totally degraded. And the government approached us to have a solution, and we have implemented watershed management and different structures of watershed treatment, like slope stabilization, diversion drains and contour trenches and drain structures, which we have seen a bit earlier. And with that, and these are the original structure. And just this was the earlier structure of that location, earlier position of that location, I used to receive a lot of runoff and it blocked the ways, and that was a tourist place as well. And people used to find difficulty in going over there, and local administration had problem in clearing those boulders and landmass, and land erosion and soil loss was a big problem there. And we have implemented series of conservation measures there, and these grid structures, all that. And with that, now the situation is improved, and now the flow is regularized, or instead of runoff, turbid runoff, and now flow is also improved, and it is spanned over the season and years. Earlier it used to be only during monsoonal flow. Now it has spanned over throughout the year, due to this watershed management and different interventions executed over there. And this was the flow pattern there before and after treatment. And post during pre-treatment period, the flow suddenly comes and it devastates the area and region. And now that flow is sustained over period, so people get good quality water for different purposes. This figure shows this reduction of debris flow between pre-treatment and post-treatment, and it has drastically reduced, and monsoonal flow also reduced, and lean period flow also increased after treatment. It means that water availability has become good for the people over there, and vegetation cover also established there. And this is similar, another example in Senji watershed. It's in another nearby watersheds. We create live models for different agencies for training and demonstration purpose. This was one another model of eroded landmass to rehabilitate, and this we applied using jute applications. And this was the barren land before, and we executed a series of check dams and gabion structures, and that retained eroded soil moving further to stream courses and improved the land situation over there. And this is another one watershed model, that is Sukkumajiri model. It's a world famous model, and this was the model which we took during 1970s, and this was the mother of all watershed management and water harvesting structures in India. If you Google that and just you put Sukkumajiri, you used to appear with a lot of information, and people took interest subsequently. We initiated in 1970s, and subsequently it has become a movement for watershed management and water harvesting to tackle the problems of soil and water problems in our country. And the problem was mainly due to this Sugna Lake is a tourist place, and this was man-made lake, and it receives something around 140 tons per hectare per annum silt flow, and almost 60% of its capacity was reduced over 10 years, and the local administration was concerned, and we were asked to implement watershed management, and we have taken up earthen bund over there, that earthen bund and dam, and we created a dam across the V-shaped valley, and that reduced the erosivity of the runoff, and that made available water for the local people for recycling, and agriculture situation also increased, and we have harvested the water, and we lay down distribution lines, and with that people got water for irrigation. Earlier it used to be rain-fed areas, and now it has become irrigated irrigation and agriculture. And this Sugna Lake catchment also improved, and this silt incoming to the watershed, this lake also reduced, and that has become a role model, and subsequently watershed management was become popular, and water harvesting and water use association and social fencing, entrusting the people with management of the local resources like these dams and water harvesting structures was created there from that point onwards only. And subsequently we have created many watershed management programs by different agencies and different outlays of fund, and all these watershed programs focuses on water harvesting. We have quantified different regions in terms of water yield potentials, which ranges between anything between 10 to 15% of rainfall can be harvested into water harvesting structures, which can be recycled for irrigation or multi-purposes. and we advocate construction of small size watershed ponds instead of making a one big water harvesting structure at the end of the drainage line, in order to make the in order to harvest the water where it is available, and we distribute the water to different regions and landscapes benefiting different ranges of farmers. So we advocate series of small size water harvesting structures instead of one big. And this water harvesting, see, people, animal also drinks, and sometimes people even drink also. That is the situation for water harvesting and distribution. And one another example is that this is river course. We identify streams in the low-lying areas, and this is the source water, and we take the water from the source and convey it through pipelines and harvest in the lower reaches, and again distribute through hydrants. So we take the springs and low-lying or upper reaches of the streams, harvest the water. If the source water is in the upper reaches, and we can lower reaches, we can create a hydrants to raise the water level, and from source we harvest and collect in a collection tanks and distribute it to the delivery or command areas. So this is also one of the model how to use the river water to irrigation, all that, and this is also has become popular, and with that our agriculture scenario and production also improved. And this is one of the such situation only, and we are analyzing the various watershed management programs executed by our institute and the country shows improvement in production and arresting soil loss and runoff, all that, and overall impact of comparing different watershed management programs also improved economic situations and crop production and reduce the soil loss. And we used to as regard to conservation agronomical practices, and I'll just glance through some of the photographs, and we experiment with the different tillages, and this is one experiment with the tillage and how it improves if it reduces the soil loss and nutrient loss and runoff, and how again how it improves the moisture conservation and production, all that. And this shows again different tillage programs and how the runoff and soil loss behaves, and different cover crops and crop geometry also we adopt according to the situation and crops, and strip crops across the slopes, and mixed crops and different mulching species, in situ and ex situ mulching also we promote, and we promote topo sequence based agroforestry agriculture system, and in the top capping of the top area, erosion prone area with forest species, and down below agroforestry and horticulture species, and subsequently agriculture, and down below we harvest the water and irrigate recycle for irrigation. And this is silvipastoral and horticultural interventions and different slopes and vegetative barriers, and this is one of the integrated farming system model we developed and demonstrated for these people. This is a rainbow, this is watermill, and water from watermill is tapped into fish farm, and fish farm water is recycled for irrigation. And this is one issue that water harvesting, how best it can be used for fish farming. Also we have demonstrated, and that area 4 to 5 tons of fish can be harvested from harvested water. And rice fish farming also we promote. And other than that, we accommodate accommodate indigenous technical knowledge. Farmers are real managers of land and water resources and soil resources, and so we listen them, we accommodate their perspectives in different structures. And in that we promote farmers first conferences in sequence in different regions. One of the conference I conducted during 2014, farmers first for conserving soil and water resources. So, and we listen to the farmers, and this is one picture that how people are extracting or harvesting fish resources in the rivers. So all that we listen to the farmers, and accordingly we refine them into the modern technical knowledge, or we advise the farmers to improve their farming situation and production. And this many projects I have handled so far, and we have evolved some techniques. technologies, and these some posters I've just glanced through. That's all. And these are some of the photos which I have been involved with reference to watershed-based fisheries development, water harvesting and fish farming and riverine management courses, and we are into the sensitizing of stakeholders and other state officials and graduate students, and we are working with farmers and we get to we are in the process of sensitizing people and evolving their techniques to work with them. And the institute launches Save Soil campaign and distribution of soil health cards, and over 60 conservation technologies have been developed, and we are focusing on Mera Gaon, Mera village. Every scientist is attached with some villages and they need to manage their resources over there for production. And this is some online softwares for design of structures and all that. And some of the technologies we have developed which are available online for us, and these are potential technologies from our institute, and we can have a collaboration with these many areas: soil health and soil carbon management, small watershed hydrology and river management, land use, land cover change, impacts, all that. We are looking for collaboration. That's all. Acknowledgement. Thank you, Vanda. Okay.
Okay, everyone, we don't have time for questions, so please talk with Murugan up in his office. You are in the office?
255.
255, yeah. Okay.